started. So welcome everyone to today's algebraic geometry seminar at the NCTS. And today I'm very happy to introduce Kyung-Sok Lee from Postech. And he will talk about symmetric products, Jacobian, and moduli spaces of vector bundles of algebraic curves. Yeah, please.
Okay, so yeah, thank you very much. So it's a great pleasure and honor to give a talk in National Taiwan University. So thank you very much for the invitation. So today I will talk about symmetric products and the Jacobians and the moduli spaces of vector bundles of algebraic curves. So, and Seung told me the first half hour should be an introductory talk to non-experts. So let me briefly introduce some terminology and some basic stuff. Is it okay? Okay. So, I mean, please let me know if it's too easy, but I mean, let me just briefly introduce what I will do. I mean, give some very basic knowledge in the first part, and for the rest of 1 hour, I will go some detail. Okay, so let X be an algebraic variety over field. So in this talk, I will work over C, and actually most of the parts of this talk will be extended to non-algebraic, I mean, algebraically closed field of other characteristics, and even I think non-algebraically closed field. But let me just work over C. And so in this talk, this bounded derived category of X will just mean this bounded derived category of coherent shapes on X. So let me explain what it is. So whenever A is an abelian category, then I can consider this category of bounded complexes, category of bounded complexes in C of objects in A, and then I can define the bounded derived category of this abelian category to be this category of complexes and localizing by localizing quasi-isomorphism. So if I invert all quasi-isomorphism, then or in other words, if I make all quasi-isomorphism into isomorphism, then this becomes derived category. So today, the main object of study is this one. So whenever I have an algebraic variety, coherent shifts from an abelian category, and I will consider this bounded derived category of coherent shifts on X. So this is a basic object. And then you might ask me why we should consider this bounded derived category of coherent shifts. So you might ask me. So let me briefly explain why this invariant is of interest. So there is a theorem by Gabriel telling us when X and Y are smooth projective varieties, and then X and Y are isomorphism as a variety if and only if its category of coherent shape is isomorphic to category of coherent shape of Y. So I mean, this is this category is, okay, let me say one more time. So this is bounded derived category of coherent shapes on X. Oh, is there any question? No. Okay. Let me keep going. Anyway, can you hear me? Anyway.
Oh yes, we can hear you well.
Okay, great. So let me continue. So, Gabriel's theorem is telling me that X and Y are isomorphism if and only if coordinate of X is equivalent to coordinate of Y. So what I mean is that you can take this as another kind of invariant of my variety, but this theorem tells me this invariant is too strong. So, when you consider invariant, you want to lose some, kind of information so we can compare different varieties having same invariant. But this theorem tell me this coherent shift category of coherent shift is too strong as an invariant, so it can't. I mean, if these invariants are the same, then two varieties are the same. So this is too strong invariant. But there is another theorem by Mukai, right, telling us when A is an abelian variety, and let me consider its dual. It's dual abelian variety. Dual abelian variety. Then one can show that derived category of A, this derived category of A is equivalent to derived category of A dual. But in general, A and A dual can be different variety. So this implies that this theorem tells me derived category is more flexible invariant than category of coherent shifts. So even though two varieties can be different, but it can have same derived category. But as you see, A and A dual are still both of them are abelian variety and having many common property. So in general, when X and Y are two smooth projective varieties, and let me assume that derived category of X is equivalent to derived category of Y. Then, as abelian variety and its dual variety have many common property, one can show that actually dimension of X is the same as dimension of Y, and its Kodaira dimension should be the same. And also you can see that you can also see that and its canonical ring is isomorphic to canonical ring and blah blah blah. So as a result, the bounded derived category of coherent shift is a weaker invariant than the category of coherent shifts, but still if two varieties have same derived category, then this implies that two varieties have many common property. And even more, there's a theorem by Bondar, Orloff, tell me that when X and Y are again two smooth projective varieties, and suppose that my Kx or minus Kx is M4. Then their theorem tell me that X and Y are isomorphic if and only if this derived category of X is equivalent to derived category 1. So anyway, you can see that this derived category is kind of strong invariant. So for Fano varieties, it's determined the variety itself. So let me just mention that when minus X is M4, then I will say this is Fano. Okay. Any question so far? So if not, let me continue. So let me go back to Mukai's theorem. So Mukai, as I told you, Mukai proved that when A is an abelian variety and A hat is its dual variety, then derived category of A is equivalent to derived category A hat. And then let me explain how he proved this theorem. So A hat can be dual variety can be considered as some, moduli space of degree zero Riemann bundles on this abelian variety. So since this is moduli space of certain Riemann bundles. So there is a Poincare Riemann bundle. Bundle on this A times A hat, and I have this two projection. And let me call this first projection P and second projection Q. And then whenever I have this situation, I can define a so-called Free-Mukai transform from this bounded derived category of A to the bounded derived category of A hat, which sends me, so whenever I have a complex here, then I send this complex, I first, pull back of my complex to A times A hat, and I tensor this P, and then I push forward this to this A dual. So if I just take pullback and taking tensor and push forward. So and then he showed that this functor is equivalence. And we call this functor to be Free-Mukai transform. So this is it. So in general, that means in general, when X and Y are two smooth projective varieties, and I have this projection to X times Y to X and Y, and suppose that I have some, shift here, then if I, then I can always define a functor from derived category of X to derived category of Y, sending whenever I have F, then I just take again pull back and then taking tensor and push forward. So by doing this, I can always construct a functor, and this is called Free-Mukai transform. So then, and this is a so-called Free-Mukai transform, and there's a theorem by Orloff saying that when X and Y are two smooth projective varieties, and then if I have a functor, exact functor from bounded derived category of X to bounded derived category of Y, which is fully faithful. So you get fully faithful and exact. Then he proved that then this exact functor should be isomorphic to certain Free-Mukai transform. So this Free-Mukai transform is quite universal. Whenever I have a fully faithful functor between two bounded derived category of smooth projective variety, then it should be represented by a Free-Mukai transform. So yeah, it's a strong, quite powerful invariant. And and then in this case, when suppose that now I have this fully faithful functor from this derived category of X to derived category of Y, and then so suppose that this is fully faithful, and then I can always prove that this functor has right, left, and the right adjoint functor. So in general, let T be a triangulated category. So now let T be a triangulated category. Then a full triangulated subcategory A, which is embedded into T, is called admissible if it has both left and right adjoint functor. And in this case, I can divide my triangulated category into two pieces. So if in this case, I can divide my triangulated category into two pieces. One is this A and this A hat. So this is collection of objects E such that in here such that home T to A is always 0 for every A. So if I collect all these objects, then this will form a triangulated subcategory. And I can always divide my triangulated category in this way. And similarly, I can also construct similar decomposition of my triangulated category into two pieces. So, I mean, this is defined in a similar way. And then anyway, I can always divide my triangulated into two pieces. And this kind of gives me, I mean, in this situation, you know, this kind gives me so-called semi-orthogonal decomposition of my triangulated category. So let me explain what it is. Position of my triangulated category. So again, let T be a triangulated category. And then a semi-orthogonal decomposition, let me write it SOD, semi-orthogonal decomposition of my triangulated category T is a pair of pair A and B, pair A and B, which are pair of full triangulated subcategories of T satisfying the following two properties. So first, there's no home from back to forth. So this means there's no home from B to A. So this must be 0. So every B belongs to B and A belongs to A. And the second property is for every T in my triangulated category, there exists a distinguished triangle, which is kind of a generalization of Schur-Dirichlet sequence in triangular category. So which sends this E, which fits into the following. There's distinguished triangle, and T must sit in this triangular category. And of course, B belongs to B and A belongs to B. So if I can divide if there's two such full triangulated categories, triangulated subcategory of T satisfying this property, I will say T admits a semi-orthogonal decomposition, and I will write a semi-orthogonal decomposition in this way. So in this case, I will write T to be A and B to denote semi-orthogonal. Okay, so any question? Okay, if not, let me continue. So anyway, this semi-orthogonal decomposition is a key tool to study, you know, bounded derived category of coordinate shifts. So let me give you several examples. Semi-orthogonal decomposition. The first result is I want to mention is theorem of Bellingson. saying that whenever I consider this bounded derived category of coherent shapes on Pn, then I can divide my derived category into n+1 pieces. There's so-called exceptional collection, and I can divide my triangulate category Pn in this way. So each piece, each piece is, I wrote this O, then this means I consider, triangulated subcategory generated by O, and this is my triangulate subcategory generated by O1 and blah blah blah, and the triangulate subcategory generated by On. So, and for this case, this category is equivalent to derived category of a point. And this part is equivalent. So, I can divide my derived category of Pn into n+1 pieces of derived category of points, and this form a natural semi-orthogonal decomposition. So this is first example of semi-orthogonal decomposition. And the second example I want to mention is work by Kapranov. Which tells me the following case. So I consider this Qn in Pn+1, and then in this case, my derived category of Qn can be written in this way. So in this case, I always have O1 to O n-1. So this is so-called exceptional collection, and each part represents each of these shapes represents triangulated subcategory generated by these shapes, and actually each piece is equivalent to derived category of point. And there is some remaining part here. So when n is odd, then there's so-called the spinor bundle on this quadric, and there's a unique spinor bundle when n is odd. So I can divide my triangulate category into n pieces of derived category of points, and so the remaining part is generated by the spinor bundle. And if n is even, so here I have same exceptional collection, but here there are actually two spinor bundles, and these even and odd spinor bundle, and so when n is even, this this also when I complement of this part, so also when I complement of this part is generated by two shapes which are two spinor bundle, and this is a work of Kapranov. So basically, basically the reason why n and odd even and odd case are different is, so if you consider quadric and you consider its maximal dimensional linear space, so then if n is odd, then actually there is one connected component of maximal dimensional linear subspace. But when n is even, then there are actually two family of linear space. For example, when n is 1, then Q1 is isomorphic to P1. So if you consider linear space, this is just point. But if you consider this two-dimensional quadric, and I'm working over C, so this is a isomorphic to P1 times P1, and there are two natural linear family of linear subspace. One is this family, and one is this family, and each of these family gives me kind of spinor bundle. And so these two, for when n is open, when n is odd, there's unique spinor bundle, and when n is even, there is a two spinor bundle corresponding to these two family. And anyway, so this gives me this two spinor bundle. And finally, let me give one more example and so there is a let me give one more example of semi-orthogonal decomposition. So there's a theorem by Bondar and Orloff. So if I consider, bounded derived category of two intersection of two quadrics, suppose that I have two quadric which intersect transversally, and then I can okay, let me go a little slow. I have one quadric and the other quadric in P2G plus 1. Then I can consider pencil generated by these two quadric. And then actually this pencil degenerate at exactly 2G plus 2 points. So there are 2G plus 2 point in this pencil. One belongs to this T1, this pencil. And then I can consider hyperelliptic curve. Hyperelliptic curve which has branch point over this this 2G plus 2 point. And this becomes a hyperelliptic curve of genus G. And a famous theorem by Bondar and Orloff tell me that actually this derived category of intersection of two quadric is generated by this 2G some number, sorry, forgot some number, I minus 1. Let me explain what this means. But anyway, this I minus 1, and so the remaining part is derived category of this hyperelliptic curve. So anyway, these are typical well-known example of this semi-orthogonal decomposition. And in general, let me explain what this number means. This I means. So this is what this number I means. So whenever I have a Fano, all these are Fano manifold, of course, as you know. So let X be a Fano manifold. Then minus KX is ample by definition. And so let me choose a maximal number such that this minus KX becomes multiple of a certain Cartier divisor. And this is called index. So this I is this I. And so whenever I have Fano manifold, then I can prove that my derived category of coordinate shape has semi-orthogonal decomposition, where this right-hand side is generated by I line bundle. And there is an orthogonal complement part. And this is called the Kuznetsov component. And of course, Sasha has many, lots of contribution in this section, but let me mention one of his famous conjecture by him. So for example, I mean this when X is smooth cubic fourfold, then this derived category of X4 is again by similar origin. You can see that there is a 3 exceptional collection of Riemann bundle, and there is this Kuznetsov component, and he conjecture that this X is rational, cubic fourfold is rational, if and only if this Kuznetsov component is equivalent to derived category of a certain K3 surface. So this is a really important and interesting conjecture in this direction. So anyway, and there has been lots of work in this direction. But anyway, you see that whenever I have a Fano variety, then there is exceptional collection of length I, and I have this orthogonal components, orthogonal, I mean, semi-orthogonal decomposition, and I will say this is Kuchness of component, and it is believed that this has very many interesting property, right? This C, like you already see that this is somewhat related to this rationality. But also this is very much related to moduli problem. Then also it's also related to homological mirror symmetry. I mean, what I mean is that in general, this bounded derived category of coherent shape is also related to homological mirror symmetry. And you can also see this is kind of totally invariant. And blah, blah, blah. So actually, this kind of semi-orthogonal decomposition is very important. Okay, so any questions so far?
So do we know anything about the decomposability of the Kuznetsov component? So in which situation we can further decompose?
Yeah,
whether
yeah.
there's this
You mean
whether there's this non-trivial SOD for the Kuznetsov component.
so I mean there can be non-trivial, decomposition, like in this case you see that this is Kuchnetsov component in this case, and this A has decomposition of S minus and S plus in this case. So I mean what I mean is that this Kuchnetsov component can be decomposed, decomposable, and well, I mean, I'm not sure if there is a nice criterion saying when Kuznetsov component can be decomposed into smaller pieces. But anyway, people think this is kind of, some kind of biggest piece of this triangular category containing information of this variety. But I mean what I can say is I mean for many examples this is indecomposable, like like this cubic fourfold, this is, in this case this is indecomposable, but as you see sometimes this is decomposable, and in any case it seems that it has many interesting information over this algebraic variety. But decomposability of Kuchnetsov component is very interesting problem, but I haven't thought about that. Yeah, thank you. Is there any further question?
And about quadric, so are there any result over non-closed field?
That's very good question. Actually, when yeah, that's very good question actually. So I think, to be honest, I haven't thought much about non-closed field case, but I mean what I mean is that actually I think for anyway this part is kind of considered as kind of even I mean shape. I consider some non-commutative variety related to this even Clifford algebra related to this quadric, and when this field is non-algebraically closed field, then I mean as far as I remember, it might be not precise, so please be careful, but this component can be somewhat non-trivial, I mean somewhat glued, because it comes from this Clifford algebra. But I need to check. Sorry for this. What I mean is that I mean when quadric is quadric is over non-closed field, then I mean this component can be changed, but in some behave a little differently. But if you want, I can send you some reference, but I At this moment, I couldn't fully remember the detail.
Thank you very much.
Yeah, thank you. Any further question? Okay, if not, let me continue. So, yeah, anyway, that's very good question. Actually, I should have thought about this non-closeness issue. But today, anyway, let me concentrate on varieties of the scene. And okay, so let me continue. So anyway, this is the end of this introductory part. Although I somewhat need to say something about motive, but anyway, let me start the main part now. So this is introductory part, and let me start. So I will say about the symmetric products and Jacobian and moduli space of vector bundles of algebraic curve, and this is based on joint works with Indrani Biswas and Thomas Gomez and Hanbok Moon and MS Narashima, who passed away years ago. Anyway, yeah, this is I want to review what we have done during last several years. Okay, so let me start. But before start, before go to this modularized space, let me again give you some kind of motivation. So there's a question by so-called Fano-Visitor problem. Visitor problem by Bondar. So asking the following. So let X be a smooth projective variety. And he asked if there are Fano manifold Y such that the derived category of X can be embedded into derived category of Y. So what I mean is that he asked if there is a fully faithful exact functor from derived category of X to derived category Y. So in this case, I will say this to be Fano-Visitor. And Visitor, and in this case, this to be Fano-Host. And we already see that why semi-orthogonal decomposition of Fano is important. So, and it has many implications to homological immunosymmetry and rationality and moduli problems. So, I mean, you already have seen several examples. For example, you see that this theorem by Bondar and Orlov saying that every hyperelliptic curve can be embedded into the derived category of Fano. And actually, this turns out to be case for many example, many case. So yes, for the following variety. Is sorry. Is so first, the theorem by Bonardara, and Lobnesh and Feinji, saying that they prove that any categorical resolution of determinant variety determinant hypersurface of general type satisfy this property. So this the derived category of this categorical resolution can be embedded into derived category of certain Fano variety. And type, and especially they prove that any smooth plane curve can be embedded into that category of Fano. And later, Segal and Thomas prove that generic quintic threefold can be embedded into that category of Fano. And later, Young Kim and In-Gyun Kim and Hwa-Young Lee and myself prove that all complete intersection varieties can be embedded into derived category of Fano. So I mean there are several more examples. But I mean there are many more. Actually, recently many people found many more examples. Anyway, so this was the this is keep going on, and anyway, so it's natural to ask when X is curved. So when X is curved, which is smooth projective curve of genus greater than or equal to 2, and then a natural candidate for my Fano host. So this is a variety of general type. I want to find the Fano variety whose derived category contains derived category of this X, and in this case is the natural candidate is this moduli space of vector bundles on curves. So let me explain what it is. So this is the moduli space of stable vector bundles of on C whose length is equal to R, and determinant is isomorphic to this fixed line bundle. And so this R and D, which is degree of this line bundle, is coprime. So why this is the natural candidate? So because first there is a theorem by Ramanan saying that this moduli space of a vector bundle is a Fano manifold of index 2. So anyway, this is a Fano manifold, and so moreover, as you see, so there's one can see that when genus is equal to 2, then the moduli space of vector bundle of rank 2 and fixed determinant is isomorphic to intersection of 2 quadric. And you see that it's already, so actually this is done by Mukai and Narashiman and Ramanan and Newstead independently. So this 3 group. Anyway, yeah, this moduli, when genus is equal to 2, then moduli space of vector bundle is isomorphic to intersection of 2 quadric. And as you see, the bounded derived category of this moduli space has semi-orthogonal decomposition, as you see, which is one component is by this theorem of Bondar and Orloff. You can see that. So this has natural semi-orthogonal decomposition. So in this case, this moduli space has this is Fano again, As you see, this is Fano manifold, and this contains the derived category of curve. And in general, when I have this moduli space of vector bundles of length R and the determinant isomorphic to L, then as you see already before, there is a Poincare bundle on this product of curve and this moduli space, and then I can define free-Mukai transform from bounded derived category of coherent shapes on X to from derived category of C to this derived category of moduli space. And in order to answer or check Bondal's question, answer to Bondal's question for curve, it is enough to check whether this functor is fully faithful. Okay, and so the natural question in order to solve this Fano-Vista problem for curve is that is this functor fully faithful? And there's a theorem by Narasimhan and Fonarev. Kuznetsov and Berman and Mukhopadhyay. Yeah, and Hambom and myself saying that actually for any rank and degree and curve, actually one can show that this functor is fully faithful. So one can actually prove that, you know, this is Fano host. This moduli space of vector bundle is a Fano host of this derived category, this curve. So yeah, I mean, actually, Fonarev and Kuznetsov Narasimhan actually prove all rank 2 case. And Fonarev and Kuznetsov prove that rank 2 and hyperelliptic curve case. And actually, they also prove general curve for deformation argument. And Berman and Mukhopadhyay prove this when genus is greater than or equal to R plus 3 and P is equal to 1. And we prove that all rank and genus and degree. So anyway, one can see that in this case, modular space vector bundle contains derived category of curve as a semi-orthogonal component, and actually this free-Mukai transform is fully faithful. So this somewhat answer this Fano-Vista problem for curve. Any question? So if not, let me continue. So anyway, then you see that anyway, this functor is fully faithful now, and the natural question is now, okay, then what will be the other component? So I already know that whenever I have a fully faithful functor, then this has a semi-orthogonal decomposition, and the natural question is, okay, then what will be the semi-orthogonal decomposition? So I already know that my derived category of vector bundle, my derived category of moduli space of vector bundle has derived category of 2 points because this is index 2 by Ramanan's theorem, and by our theorem one can see that it has one component, and what will be the S? What will S? So this is my component A, and this is my B, and how can I describe the other component B? Is what? And then there's conjecture by Narasimhan and Berman and Garkin and Mukhopadhyay. So they have the following conjecture. So derived category, so they independently conjecture the following thing. So derived category of moduli space of vector bundle of rank 2 and determinant L have the following sinusoidal decomposition. 2 points and derived category of 2 curves. And derived category of 2 copy of G minus 2 symmetric products of curve and 1 copy of derived category of 1 copy of G minus 1 symmetric product of curve. So here CK means symmetric product of curve. So I product C K times, and then I divide this by the symmetric group of K elements. So, then this becomes symmetric products. So anyway, we have this conjecture, and so let me explain more detail and the recent progress about this conjecture later. But anyway, another natural question is, how can we understand this semi-orthogonal decomposition? So what this semi-orthogonal decomposition will tells us. So what is the meaning of this semi-orthogonal decomposition? So how can we understand this? And actually, when you see these references of semi-orthogonal decomposition, you say that it is written some reference. It is written that this semi-orthogonal decomposition can be understood as kind of non-commutative motivic decomposition. And actually, Orloff have the following conjecture. So if X and Y are smooth projective varieties, sorry, I was in a rush a bit, but then I make some mistake. Okay, anyway, so let X and Y are 2 smooth projective varieties such that its bounded derived category of X is equivalent to bounded derived category of Y. Then he claimed that, he conjectured that the motif of X is isomorphic to the motif of Y, or the effective Char motif, the category of effective Char motif. And he also conjectured that if X and Y are smooth projective varieties, X and Y are 2 smooth projective varieties such that the derived category of X is embedded into the derived category of Y, or there's a fully phased performator from derived category of X to derived category of Y, then its Char motif, this Char motif of Y is isomorphic to Char motif of X times some Lespechan motif plus some top. So what I mean is that if there is a fully phased embedding from derived category of X to derived category of Y, then he conjectured that Char motif of Y contains Char motif of X as a direct component, direct summand. So this is his famous conjecture. And okay, let me briefly explain what motif is. So, motif, the category of motif is when Grothendieck developed the theory of ethyl cohomology and crystal cohomology, he wants to understand the behavior of, the origin of same behavior of cohomology theory. So he suggests that there is kind of the theory of motif to explain the common behavior of this different cohomology. So the rough idea is I consider smooth projective category of smooth projective varieties, and then varieties, and I consider this category of smooth projective varieties, and I have this Bayes cohomology theory. Then this is K plus And then, I mean, different cohomology behave similarly. So he suggests that there is a category of motifs, whatever it is, and then this fail cohomology or factors through this one. So for example, this Q-ness formula, for example, this motive of x times y is, what I mean is that this motive of x times motive y is isomorphic to motive of x times xy, and this explains Q-ness formula. Why are these making so yes. And similarly, one can explain the similar behavior of different cohomology using this category of motifs. So this is his motivation, and he constructed the Chow motif, the category of Chow motifs, as you know, first I consider this as in this way. So I mean, this first one can consider this category of correspondence. So this is a category whose object is smooth projective varieties of field, and you know, morphism from x and y is actually Chow group or dimension with this product, and sorry, rational Chow group. And then, you know, by this, starting from this correspondence, one take pseudo-abelian closure to construct this Chow motif, effective Chow, category of effective Chow motif. So, which taking pseudo-abelian closure means every projector have, you know, corner and image, and it becomes a direct cement. And by inverting formally inverting Lefsetz motif, one can define this category of Chow motif. And one can show that actually this category of smooth projective varieties is functor from this category to category of motifs. So anyway, this is a motif, and what I want to, I mean, this is the motivation of motif, theory of motif, and actually Orloff conjectured that the derived category and motif will behave similarly, especially when two smooth projective variety have same derived category or equivalent derived category. Then he conjectured that the motif of two category is isomorphic, and when there is a direct cement, when there is an embedding, then this motif of y contains motif of x times of Lefsetz motif as a direct cement. Okay, then from this perspective, let me see this conjecture. So this conjecture by independently suggested by Narasimhan and Berman-Gatti-Mukhopadhyay, saying that this from perspective of Orloff, one can ask what is the meaning of this semi-orthogonal decomposition. And then I prove the following theorem. So actually I intensively use work of Nervanu, saying that in any semi-simple category of motifs, we have the motif of this moduli space of rank 2 vector bundles, it's rank 2 vector bundles on this curve has the following, the motif of this moduli space has the following decomposition. So I can, its component is symmetric product of curve tensor with the L to be this Lefsetz motif. Okay, plus one copy of G minus one symmetric product times So I mean, I proved that in any semi-simple category of motif, one can has that the motif of moduli space can be decomposed into, as you see, there are two copies of symmetric product of curve from K1 to G-2, and there's one copy of symmetric product G-1 symmetric product of curve. And this is, you can see that this is compatible with this conjecture. Okay. And later, yeah, so later, people found the similar, isomorphism. So this was, I mean, Bellman and Garkin and Mukhopadhyay proved that this similar identity in the cross and ring of variety, but up to certain toজন. Similar identity, but up to toজন, which is supposed to be zero, but I haven't following recent development, but anyway, there's some similar decomposition in the level of this cross and ring of varieties. And so anyway, this you can see that this motif and derived category behave similarly. And then I and Narashiman prove that under certain technical conditions, so if genus is greater than 16 and this is non-hyperelliptic curve, one can see that then the derived category of curve second symmetric product can be embedded into the derived category of the moduli space. And so we somewhat proved the symmetric product also can be embedded into the derived category. And then later, this was, I mean, enhanced a lot. So there's theorem by Tebelev and Torres. And later Tebelev completes their work. Let me explain what it is. And Su and Yao actually proved that the derived category of this moduli space of vector bundle has expected semi-orthogonal condition. So let me explain. So what I mean is that, so they prove that the conjecture is true, especially Tebelev and Torres and Su and Yao prove that this there is such a component embedded into this derived category here. And later Tebelev proved that actually these components generate the whole category. So there's no remaining, no orthogonal complement. So first they prove that derived category of moduli space has this expected component. And later, Tebelev proved that this is the whole. So there's no orthogonal complement. So this is the whole category. So anyway, for rank 2 case, now we understand the semi-orthogonal decomposition of the moduli space of vector bundles on curve. Okay, any question?
So yeah, maybe I would like to ask a question about some earlier statements. So okay, so you say that using this moduli space of a vector bundle, so as a corollary, a smooth projective curve of genus larger than or equal to 2 is a Fano visitor.
Right,
and,
right.
So for genus equal to 1 is plane curve. And in this case, what is the Fano visitor of elliptic curve?
Elliptic curve. So actually, this for elliptic curve, the construction is quite simple. You first embed this elliptic curve into some big dimensional projective space. And you write this, well, there's a so-called, anyway, this was done by, this work of Bernarda and Bologneshi and Feinji and myself. But anyway, the its essence is first write down this elliptic curve as zero locus of a certain vector bundle on big projective space.
Mhm.
And then you projectivize this vector bundle. And then there's a corresponding line O1 line bundle on this projectivized vector bundle.
Hmm.
And actually the section which gives this elliptic curve gives me a section on this line bundle on this projectivized vector bundle.
Mhm.
And if you consider, the zero set of this projectivized vector bundle, then this becomes Fano host of this elliptic curve.
Hmm.
So anyway, for elliptic curve case, because it can be written as a smooth plane curve or a complete intersection, one can see that this actually, the Fano host is constructed explicitly.
Hmm. Also,
Yeah.
another question is that usually, what are the techniques to show that some functor is fully faithful? For instance, in this statement, or or just a DBC inside.
So that's very good question. Actually, when this there is again by theorem by Bondar and Orloff, which is one of the standard technique of showing fully faithfulness. So Bondar and Orloff. So basically, the theorem is something like so let X and Y be smooth projective variety. Then anyway you know that if there is a fully faithful functor by Orloff's theorem, it should be a free Mukai transform. So then I know that suppose that if I want to prove some functor is fully faithful, first it should be written in terms of a free Mukai transform. So I should say that this is kind of there is some object in the product, and then you see that this Priya-Mukai transform gives me this term from this here, and then the theorem of Bondar and Orloff saying that to check fully faithfulness, it's enough to check this for skyscraper shift. So what I mean is that you consider this skyscraper shift here, and then you consider its image. But then each image is something like this one. So, I have X, and I have Y, and I have this X times Y, and I have this two projection. And suppose that I have a skyscraper shape, and then the pullback of this is this Y, isomorphic to Y. And then I have shift E here. So usually, in our case, it's usually vector bundle. And then, if I have shift on this X times Y, but so if I consider skyscraper shift and taking pullback, then it's something like this E restricted to this X times Y. And then Y is, let me call it EX. And let me define this to be, let me call it this to be EX. And then since, this is isomorphic to Y, it's push forward is just the EX. So anyway, this skyscraper shift goes to EX. Then by the famous theorem by Bondar and Orloff is telling you, in order to check this is fully faithful, one need to check if it's this is a fully faithful in the level of skyscraper shift. So in order to check this is fully faithfulness, I need to check that derived category of skyscraper shift is isomorphic to. So what I mean is that here I need to shift, and this is isomorphic to from Y, X, prime shift. So if I can prove this isomorphism for every 2 points and every I, then this is fully faithful. So usual technique is to check, fully faithful in the level of skyscraper shift, and this part is easily described, and so then you need to compute the cohomology here, and this is usually a difficult part. But anyway, if you check this is the same, then This is usually difficult, but anyway, this is the standard technique to prove fully phased premise.
Thank you.
Yeah. Any further question? So let me continue. So, well, okay. So I told you about this, length 2 situation, and then the natural question is now, what will be the semi-orthogonal decomposition of derived category of moduli space of vector bundle on higher rank? So, by our theorem, we see that this moduli space of a higher rank vector bundle also contains curves. So it is a natural question if what will be the semi-orthogonal decomposition. And from this perspective, Thomas and myself have the following conjecture. The derived category of this moduli space can be decomposed into part where this component is equivalent to some product of symmetric products and the Jacobians. I mean, of course, we sometimes don't have Jacobians and sometimes don't have curve, but anyway, yeah. So anyway, each component can be written in terms of symmetric products of product of symmetric products of curve and Jacobian. And why? Actually, it's quite natural to expect such thing because first, let me tell you why we have this conjecture. There's a theorem by myself and Thomas. So let me explain this one. So if I consider some motivic Poincare bundle, motivic Poincare polynomial. So let me not explain this, but I mean, this is kind of all the characteristic of motifs. So anyway, if I consider this motivic Poincare polynomial for this rank 3 vector bundle, then one can see that this can be written as times L So this can be decomposed into the following way. So sorry. Okay, this is right. So I can always find the kind of motivic composition like before, but in this case, so anyway, one can see that for rank 3 case, one can see that our motif for this rank 3 vector bundle can be decomposed into motif of product of symmetric products and product of symmetric product and this one. So you can see that each component is product of symmetric products, and for rank 3 case, one can see that the motif of this moduli space can be decomposed into this motif of some of the motif of symmetric products. And we prove this for motivic Poincare polynomial, but later, this identity was enhanced by Fu and Hoskin and Lehalla. So they enhanced this to the category of rational Chow motifs. So one can see that actually this motivic decomposition is it is true for rational Chow motifs. So, and this is one reason why we have this conjecture, and there's another reason why self. I mean, this is I think many people expected this one, but anyway, we wrote this in our paper. That so when k is less than or equal to g minus 1, then one can expect that the derived category of symmetric product does not admit a non-trivial semi-orthogonal decomposition. So we somewhat expected this one, and actually this is now proven. So by Biswas and Gomez and myself and Bastel, sorry, go slowly. Bastianelli and Bermans and Okawa Shinosuke Okawa and Ricorfi. And this was completed by actually Sun Lin. So in our case, we prove this when this is when k is less than gonality of C, and the gonality is actually kind of minimal degree of this map from this curve to K1. So this gonality, and this is usually this number for general curve. So anyway, when k is less than gonality, we prove this conjecture, and Bastianelli and Berman, Okawa, and Ricorfi prove this when they develop some deformation argument, and they prove that this is the case. So for this number, so using deformation argument, and actually Sun Lin prove all the case. So anyway, one can see that this symmetric product, which is when k is less than or equal to g minus 1, then this derived category doesn't admit the semi-orthogonal decomposition. So we somewhat, it's kind of a similar situation like in the representation theory. So every representation can be decomposed into irreducible representation. So this is kind of irreducible component and indecomposable component, and then we can see that this can be indecomposable. And actually Sun Lin also proved that. So he anyway proved all this for all case, and derived category of CK1 times A times Jacobian times Jacobian also does not admit a non-trivial SOD. So I mean, from this analogy of representation theory, one can expect that it is quite natural to expect that this component, each semi-orthogonal component can be written in this way.
What are the assumptions on the number of components or any number of products? And
Any
K1
number of product, and each ki is less than or equal to g minus 1.
Mhm.
So I mean, if each component is indecomposable, and the Jacobian, it is known that Jacobian also doesn't admit the non-trivial semi-orthogonal decomposition. And what Sun Lin prove is the products of all these things also do not admit any non-trivial semi-orthogonal decomposition.
So if we replace the product of Jacobian by just any abelian variety, so so do you
then it doesn't admit the semi-orthogonal decomposition.
So you can replace the product of Jacobian by any variety, abelian varieties.
I think so. Sorry, I should check Sun Lin's paper, but he developed a very powerful technique to prove this non-indecomposability, and I think more or less he proved that. But let me be careful. But for any number of Jacobian, it works.
Okay.
And for any, of course, And the abelian variety should be the case because in general, Calabi-Yau variety does not meet
Yeah,
the
yeah.
semi-auxiliary decomposition. So, I mean, Calabi-Yau case, it doesn't matter. And the product, so what I mean is that product of abelian variety or Jacobian doesn't, since this is Calabi-Yau, will not admit any non-trivial semi-auxiliary decomposition. And for product of symmetric product, one need to check Sunlin's paper, but I think he developed a very powerful method, so I think it should be true. But yeah, but let me I haven't checked the detail, so please, I mean, but anyway, one can see Sunlin's paper to see.
Okay, thank you.
Okay, thank you. So anyway, this is somewhat expected. And anyway, one can believe that the symmetric products can be embedded into the category of moduli space. And let me quickly finish my talk by mentioning several theorems. So there's a theorem by Hanbom and myself saying that if rank is greater than 2k, then we can prove that the derived category of K-symmetric product for arbitrary number. So arbitrary K, for arbitrary K, if rank is large enough, the derived category of symmetric product can be embedded into the derived category of moduli space of, rank R vector bundle. So we prove that as a corollary, one can see that all the symmetric products and Jacobians are phonoviston. So one can see that every symmetric product and Jacobians are phonoviston. So we can prove this visual. And let me give you one more remark. So almost more interesting development. So one can see that by anyway. So we see that derived category of symmetric product can be embedded into derived category of moduli space and its Fano variety. And from philosophy of Orlov or conjecture of Orlov, we can ask what happened to motifs. So one can ask a smooth projective variety X is a motivic phonoviston if its motif tensored by some Lefschetz motif can be embedded into motif of Y as a direct summand, or from anyway is a direct summand of motif of Y where Y is a Fano manifold. So one can, it's just it's completely analogy of this conjecture of order. And by analyzing the the motif time I and Hanbom prove that all the symmetric product and Jacobian are motivic phonoviston. So we can actually, see the motif of moduli space of vector bundle, and we can see that all the symmetric products in Jacobian are motivic phonoviston. So yeah, we use the work of Bano and myself and Gomez and Hu and Hoskin and Lehala. Anyway, combining all this work, then we can prove that these symmetric products and Jacobians are motivic phonoviston. And there's one more remark here. So there's a theorem by BR saying that when V and W are smooth projective variety, and when there is a surjection from V to W, then actually one can see that the motif of V contains motif of W plus some alpha. So what I mean is that this motif of W can be understood as some direct summand of motif of this V. And again, there's a almost theorem by Matsusaka saying that every abelian variety admits a surjection from Jacobian of curve for some curve C. Sorry, I'm a little rush. So and then by theorem, by the proposition of Hanbom and myself, we can prove and combine these two theorems by BR and Matsusaka. We can prove that every as an easy corollary, every abelian variety is a motive. Okay, so we can prove that any abelian variety, its motive is embedded into motive of some Fano variety, especially this motive of the moduli space of vector combination curve. Okay, that's all I want to say. And thank you very much for your concentration. Thank you.
Oh, thank you.
Yeah, thank you very much.
So are there any questions? So for instance, in the in the rank 3 case,
Yeah.
so your formula of Poincare polynomial, there is no Jacobian involved.
Yeah, exactly. Yeah. But
So
actually, I mean, that's true. But I mean, in that case, we can write everything in terms of symmetric product. That's true. But actually, for some symmetric product, it can be also decomposed into Jacobian. So what I mean is that in this case, this each component is not irreducible. What I mean is that if K is sufficiently large, for example, let me see this. Let me go back to this case. So you see that when K is for this case,
larger than G.
Yeah, larger than G, then its derived category and also its motif can be decomposed into motif of Jacobian and the motif of symmetric product, smaller symmetric product. So yeah, in this sense, Jacobian also appear. And for higher rank case, we expect Jacobian also appear. So yeah. Anyway, in this case, we can write out everything in terms of symmetric product. That's the case. But we can further decompose this into Jacobian.
So when the rank is higher than 3, it's not known, so maybe complicated.
Yeah, it's not that easy, to be honest. I mean, it's complicated and yeah. I'm working with a student on this, but I mean, it's not. It's quite complicated.
Okay, so are there any questions? Yeah, so it seems that the okay, so VR result gives a geometric some geometry way to produce kind of a visitor, but it seems that also if we replace child motif by derived category, then difficult to difficult to find a systematic way to find such a visitor.
Right. And even we can't say this any abelian variety is a Fano visitor yet. So what I mean is that we prove every Jacobian is a Fano visitor.
Yes.
But for any abelian variety, we can't say because this theorem can't be. I mean, for example, let's consider this BR's case, and suppose I have a surjective map from Jacobian to an abelian variety, but it doesn't give me a semi-orthogonal decomposition in the level of derived category.
Because we need the push forward of the structure sheaf is
exactly. So derived push forward of structure sheaf is not structure sheaf anymore. So we can't say this is fully faithful. I mean, and it's not, it's not fully phase friendly. So what I mean is that this derived category of, you know, Jacobian does not admit any non-trivial semi-axiomatic composition. So yeah, I mean, there is, you know, this is slightly, I mean, this is some different behavior between this derived category and you know, motifs. So I mean, what Olof is telling us that when something happened in the level of derived category, then we somewhat expect something happen in the level of motifs, but not vice versa. I mean, yeah, that's interesting. You know, some discrepancy here going on, and one needs to understand this more. Yeah, but at this moment, I don't know. Yeah.
Yeah, again, so I think fully faithful embedding is difficult to find.
Yeah, that's in general quite hard because you need to check this for even checking this for skyscraper shift is not easy. Yeah.
Are there more questions? So if there's no more question, then let's thank Kyung-Suk again for his very interesting talk. So thank you very much.
Yeah, thank you very much. Thank you.